I wanted to give you some direction on how to use the data that you collected from your chromatography experiments and how to work with some of those numbers. So if you watch, I will kind of guide you through what some of your numbers may or may not look like and what you need to do with them. Now, just a second, let me get my tablet up and running. So the first thing is that on your data sheet, you should see a couple of different things, or on one of your data sheets. You have a 595. So an absorbance at 595 nanometers. And in a column adjacent to that, you see protein concentration. Now that protein concentration, naturally a fair question is, how am I supposed to take an absorbance at 595 nanometers and calculate a concentration or your protein concentration? Well, let's go ahead and get some hypothetical data. Let's say 0.426. Now, to get a concentration from this number, what you're going to have done previously is a Bradford assay. A Bradford assay where we have a plot that looks a little bit like this, we'll say. And from this, you came up with a y equals mx plus b, a line of best fit or an equation for that. Your y-axis for this graph will be your absorbance at 595, and then your x-axis is going to be protein concentration. Now, the units for protein concentration will be micrograms per microliter. And your A595, that's an absorbance, and therefore it has no units. Now, with that in mind, where did you come up with this? You came up with this graph in experiment number, I believe it was experiment number 2 or 3, where you had protein samples with known concentrations, and you calculated an absorbance from those. So you were able to put together this graph during experiment number 2 or number 3. So the data that you collected through chromatography, that's going to be something that you take this, say the 0.426, and you plug it into a previously solved or previously produced y equals mx plus b. And you're going to plug that 0.426 into your equation for y. So let's say hypothetically that you have an equation that is y equals 0.5176x plus 0.0041 or 0.0041. So let's say that's our equation for our line of best fit. What I'm going to do is I'm going to take my 0.426 and plug it in. So 0.426 equals 0.5176x plus 0.0041 and simply solve for x. So I'll subtract my 0.0041 minus 0.0041, and that gets me, let's see, 0.426 minus 0.001, 0.4219 equals 0.5176x. Divide each side by 0.5176. 5176, and I ultimately get from that x is equal to 0.815 micrograms per microliter. So that is going to be the answer for that value. So I'd write in 0.815. Your values might vary quite considerably. It all depends on what your equation for your line of best fit is. All that you need to do, and you can automate this with Excel, is plug in the A595 value for that Y and solve for X. So yeah, you can manipulate Excel to give you that equation and solve for X for every single one of those columns. And that will give you a sense of how much protein is in each one of those samples, or what the concentration for each one of those samples is. Now, this is effectively what you're going to be doing for your practical final exam. You're going to use a series of unknown samples and determine the concentration for a protein. Or sorry, you're going to use a series of known protein samples, and based on those known samples' absorbances, determine the concentration of an unknown sample. All right, so that's one of the components. Another component, and so let's actually, I'm going to erase not all of this, but some of this. This. Go. Okay. What I need to save, what I need to preserve is that 0.815, erasing most of this, but not all of this. Okay, so shoot. So I'll table this information right up here. So let's say this exact same sample, you did a catalytic assay on it. And for that catalytic assay, you measured A340, so absorbance at 340 nanometers at several different time points. 0 seconds, and let me erase that. 0 seconds, 15 seconds, and 30 seconds. So A340 for each of these time points. Now, let's say hypothetically we got a value of 0.012, 0.066, and then finally 0.091. So this gives us a delta, or a change, in 340, and it gives us that change in 340 for a particular time point, or for a time range, and that would be 0.5 minutes. Okay, now what we can do with this information is we could go ahead and we could calculate, well, what's our difference? What's our change? Our A340 per 0.5 minutes is going to be 0.091 minus 0.012 divided by 0.5, or half a minute. So do the calculation on that. 0.091 minus 0.2 divided by 0.5 gives me 0.158 per minute. Now, the thing is, what's sort of complicated about this is a valuable number, but it's also like we're looking at simply the change in absorbance. The change in absorbance alone is not extremely valuable. We have to correlate that change in absorbance to something valuable. And we use what's known as the Lambert-Beer law, or Beer's law, which has an equation that is A equals LC. Absorbance is equal to an extinction coefficient, EXT, coef times the path length, which our path length is 1 centimeter, because our cuvettes are 1 centimeter, so the light shines through 1 centimeter of our sample. And C ultimately is concentration in molarity. So we can look at our change in absorbance and relate that to, well, the concentration of one of our products, and one of our products that we are able to detect with light at 340 nanometers is none other than NADH. So how we go from, or how we use this number is a little bit complicated, because what we're going to be able to do is convert this from absorbance units per minute. So basically you could say AU per minute to millimole per minute to units of LDH activity. So that's kind of our progression. This absorbance units per minute we have. Now, when we talk about an enzyme, we define an enzyme's activity. So 1 unit of LDH activity is 1 millimole NADH per minute. Okay, so that's our definition for 1 unit of lactate dehydrogenase activity. So another way you could phrase that is, if you have 200 units of lactate dehydrogenase activity, that means that that sample that you have can generate 200 millimole of NADH per minute. So we have basically that. We have the bridging a gap from millimole per minute to units of LDH activity. So we've got that. What we don't have is this right here. So we don't have our direct connection from absorbance units to millimole. However, or sorry, we haven't defined that yet. We have that, and the way that we have that is with Beer's law, or the Lambert-Beer law. Now, the first thing that I'm going to do is I'm going to take this 0.158. So my absorbance units. What I'm going to do for the time being is I'm going to ignore the unit in my denominator, which is minutes, because that's constant. That is consistent throughout all of my different definitions. What I need to worry about and what I need to be thoughtful of is converting my absorbance units, the 0.158, into millimole. And so the way that I'm going to do that is I'm going to need to know this extinction coefficient. That extinction coefficient is 6,220. Units are inverse centimeters, inverse molar. So one of the ways that you could think about that is if you take your extinction coefficient and you multiply it by our path length, which is 1 centimeter. And then you multiply it by our concentration, which is in molarity. Effectively, we will have these units all cancel one another out. So what we are going to do, though, is we are going to figure out our concentration. So we are going to take that 0.158, set that equal to ELC. E is 6,220. L is our path length, which is 1 centimeter. C is our concentration, which we know the units for it, it's molarity, but we don't know that number. So what we're going to do is we're going to take 0.158 and divide it by 6220 times 1. And that is ultimately going to be equal to C. So I've really just plugged numbers in for E, our extinction coefficient, and L. So we've got 0.158 divided by 6220, which is going to give me a concentration. I'll plug in my calculator. 0.158 divided by 6220. That's going to give me a concentration of 2.54 times 10 to the negative 5th molar. Now, I don't want, so I've gone from absorbance units to molarity. If we look at absorbance units up here, kind of our flow chart, we're going from absorbance units to millimole. So we've gotten a little bit closer to where we need to go. We're now speaking in terms of moles, but millimole is a discrete quantity compared to molar, which is a concentration. Now, if ever you're given a concentration and you want a specific quantity, well, for instance, if you want to go from molar to moles, you have to know the volume that we're talking about. So here, what we can do is go from molar to moles. How? Well, you have to know the volume. And we know the volume of our overall reaction. Our overall reaction, it was 1,000 microliters, or 1 milliliter. Everything was all mixed up. The volume in our cuvette was exactly 1 milliliter. So I'm going to take my 2.54 times 10 to the negative 5th and multiply it by 0.001, because that is 1 milliliter. 1 milliliter is equal to 0.001 liters. So I'll take that, again, that 2.54 times 10 to the negative 5th and multiply it by 0.001. Now I have approximately, do some erasing real quick. That gives me, let's see if my calculator. This actually just gives me 2.54 times 10 to the negative 1, 2, the negative 8 moles. Okay, so now I've gone from absorbance units to molarity to a concentration by using the Lambert-Beer law. Then I use the volume of my reaction to get the number of moles that are generated. And now I just need to go from moles to millimole. Now, in 1 mole, there are 1,000 millimole. So 2.54 times 10 to the negative 8th. And I get 2.54 times 10 to the negative 5th millimole. So that 2.54 times 10 to the negative 5th millimole. Now the second part of this, well, maybe not the second part, but we just have to look back and remember what were the units that we were talking about. We were talking about millimole per minute. And so we omitted that time because it was consistent. So I'm just going to add this back in. This is per minute. Okay, so what that means is in the fraction that I was talking about, I had 2.54 times 10 to the negative 5th millimole per minute, or millimole of NADH generated in every minute. So what that means is I also have, because my definition at the top, 1 millimole NADH per minute is equal to 1 unit of LDH. I have 2.54 times 10 to the negative fifth units of LDH activity. So that's a valuable number that I just figured out. How many units of lactate dehydrogenase activity were in this specific sample? So this gives us a definition for the amount of lactate dehydrogenase activity is in that specific sample. What I'm going to do is I'm going to move that up here. 0.54 times 10 to the negative fifth units of LDH activity. I'm going to move that to the top because this is a number that I'm going to revisit. In the meantime, I'm going to erase everything real quick. So now what we're going to be able to do is we're going to use our protein concentration and our units of activity to solve for what is known as a specific activity. Our specific activity is arguably the number that really matters. So that was our specific activity is defined as units of enzyme activity per amount of protein. So the way that we should treat this is we know the units of LDH activity in that specific sample, and we also know the protein concentration in that specific sample. So what we need to do is say, all right, well, we have a protein sample that has a concentration of 0.815 micrograms per microliter. Now, we know that whenever we added our protein sample to our cuvette, it was 900 microliters of Bradford reagent and 100 microliters of protein. So what we're going to do is we're going to take this 0.815 micrograms per microliter and multiply it by multiply it by 100 microliters. And that will give us our micrograms of protein. So 0.815 times 100 would be, go ahead and scribble this out, 81.5 micrograms of protein. Now, have we defined this as knowing exactly what that protein is? No, we haven't. But what we're going to be able to do is look across multiple samples and say, okay, well, there's 55.6 micrograms of protein in this one, and there's 81.5 micrograms of protein in this one. Now, what we want to do is compare the amounts of protein to the units of enzyme activity. So I'm going to, and that will give us a little bit more insight into which sample has the most lactate dehydrogenase. And the sample that's most enriched for lactate dehydrogenase is your sample that has the highest specific activity. So I will take my 2.54 times 10 to the negative fifth units of LDH activity, divide that by 81.5. And I will go plug that into my calculator. 2.54 times 10 to the negative fifth. Divide that by 81.5. And that gives me 3.1 times 10 to the negative 7th units per microgram. So this gives us our specific activity. This is going to be used for comparison amongst all of your samples. Which one has the highest specific activity gives you more insight into which protein sample has the most lactate dehydrogenase. So from the data that you collected, you should be able to figure out A595, what is your protein concentration? Then, what are the units of LDH activity? And then finally, if you know those two things, the concentration of protein, the units of LDH activity, what is the specific activity? All right, well, I hope that was helpful, and I hope that you have a good day.